In this video, I want to talk about some variations of the state elements that we saw so far. So the first thing that I want to talk about is that usually in practice we don't have, let's say, only one D flip-flop for storing one bit of a state. Usually what happens is that we have a bunch of flip-flops that work with exactly same clock signal, and they are used to store several bits of state information. So for example, in a digital clock, how many state bits do you think you need to have? So depending on whether you want to show the hours, the minutes, the seconds, right? For each one of them, you probably need to have several bits to represent each one of them individually. But all of them should work with exactly the same clock. And that is the main reason for having the concept of synchronous sequential circuits. So usually what happens is that when you have a bunch of D flip-flops or flip-flops in general that work with the same clock signal, you consider them as registers. So this is a symbolic representation of a 4-bit register. So as you can see, we have the clock signal, and as you can see, this clock signal is going through all of these clock inputs of these individual D flip-flops. For each one of these flip-flops, we have their own associated input signal, and each one has their own associated output signal as well. So let's say you want to use this register to store values between 0, 0, 0, 0 and 1, 1, 1, 1, because we have 4 bits of information as the input and 4 bits of information as the output. So this can be D0, this can be, this is D1, this is D2, and this one is D3. So to avoid complicating things when we want to draw these, it is very common that we use a shorthand representation for such a register. So we have D3:0, so that means that it has 4 components: D3, D2, D1, and D0. We have a bus, which we show it with this slanted line, and we write 4 on top of it that represent that this single bus contains 4 lines of information. And for the output, we do the same thing. So we have Q3:0, which means that we have Q3, Q2, Q1, and Q0. And then we have this bus with this slanted line that shows we are working not only with a single wire, but a bunch of wires. And how many wires? This value shows that we have 5 wires too. So that is one variation that we usually consider when we work with more than a couple of D flip-flops. So there are other types of flip-flops as well. So the first type that I want to talk about is the enabled flip-flop. So think of it this way. What if you have a bunch of memory units or states that you don't want to touch, right? So isn't it nice to have a signal to basically disable a bunch of these states? So when the time is appropriate, you let those states to be changed, whether needed or not. So that is the main reason behind having an enabled flip-flop. So this gives us an additional level of control over whether we want to store any state or not. So in the enabled flip-flops, we use an enabled input that controls when new data is stored. So just because we say that we have this enable input that controls when the new data is being stored, don't confuse this enable input with the clock. Because we know that the clock signal can be used to control when data is being stored, right? So this one is giving us a higher level of control, whether some of our flip-flops are even in the loop or out of the loop, right? So because you can imagine when the system's getting more and more complex, having only a couple of D flip-flops won't be enough. But at the same time, since our system may have several components, there are times at which we don't even want to touch a set of flip-flops, right? So that is the main reason behind having these type of enabled flip-flops. So how do you think we can design such a circuit? The answer is very straightforward. So similar to when we work with the enabled buffer, in which we had one A as the input and Y as the output, and we had this enable signal. So whenever enable signal was 0, that was basically equivalent to this buffer not being connected at all, right? It was considered to be completely off. But as soon as the enabled signal was on, then whatever A we had, we could see it in Y. So the same concept can be applied to the enabled flip-flop too. When enabled signal is 1, then D passes through to Q on the clock edge. When enable is 0, the flip-flop retains its previous value or previous state. So the design of such circuit can be done by using a multiplexer, more specifically a 2-to-1 multiplexer. You remember we use multiplexers to select between some inputs. So this 2-to-1 multiplexer has two inputs, one control input, which is the enable signal itself, and one single output. When the enable signal is 0, this input is going to be selected to be delivered to its output. So this is when enable is 0. And what is this input? As you can see, it is connected to Q. So when enable is 0, that means that we don't want this flip-flop to be changed. So whatever it was previously, we want it to stay at its previous value. On the other hand, when enable is 1, this input will be delivered to the output of the multiplexer. So this input is connected to the data that we want to be stored. So when that happens, this data will be selected in this multiplexer and will be delivered to the data input of the flip-flop. So the main reason that we do that is we usually don't have that much control over clock. We don't change the rising or falling edge of the clock on the fly. We usually have this as a frequency, a specific fixed frequency that basically fluctuates between 0 and 1, right? So let's say if we decide this to be 1 kilohertz, that means that it is doing this thing going from 0 to 1 and then 1 to 0 1,000 times per second, right? So since this is fixed, it is nice to have some control over when we actually want to store anything on the flip-flop. So that was one variation of flip-flops. The other variation is the class of resettable flip-flops. So let's say you have a bunch of flip-flops that you want to be able to control with one single input. And you want to make all of them to be 0 whenever you use that signal or single input. So one way to make all the flip-flops to be 0 is to write 0 on each of them, right? But this gives again more control. By changing one signal, one input, you have that functionality. You want to have that functionality. So in the resettable flip-flop, whenever reset is 1, Q is forced to 0. Whenever reset is 0, flip-flop behaves as it was behaving before. So it works as an ordinary flip-flop. So the symbol for a resettable flip-flop is like this. We have the data input, we have the Q output, we have the clock, and then we have this additional input, we call it reset. So now with the resettable flip-flops, there are two possible cases that can happen. We can either have a synchronous resettable flip-flop, or we can have an asynchronous resettable flip-flop. So a synchronous resettable flip-flop basically resets the flip-flop on the clock edge. So as you can see, when you change the reset signal to 1, the change in the Q does not happen instantaneously. It waits for the next clock edge, and on the next clock edge it makes the output 0. On the other hand, for the asynchronous resettable flip-flops, as soon as you change the reset signal from 0 to 1, you basically immediately force the output to go to 0. So based on these differences, there are different ways to design these two types of resettable flip-flops. So for asynchronous resettable flip-flops, you need to make some changes to the internal circuitry of the flip-flop. But for the synchronous resettable flip-flop, the design is very simple. So you might ask, how can we do that? So this is the internal design of a synchronous resettable flip-flop. As you can see, when the reset signal is 1, that makes reset bar to be 0. That makes the output to this AND gate to be 0. So when you make reset to be 1, you make the data input of the flip-flop to be 0. But this change won't be reflected in the output Q of the flip-flop until we get to the rising edge of the clock. So as soon as we go from 0 to 1 on the clock, this change will be reflected. So let's say we have this clock to be something like this. So this is the clock. This is the reset signal that goes from 0 to 1, let's say at this point. For the synchronous flip-flop, let's just say we have the output either can be both 1 and 0. So since we don't know what was its previous value, I'll just show it as both of them, right? So as soon as we get to the rising edge of the clock, the output becomes 0. So this is for the synchronous resettable flip-flop. What about for the asynchronous one? For the asynchronous one, as soon as we make the reset signal go from 0 to 1, we basically change the output. So this is the main difference between these two types conceptually. As for the implementation, the synchronous resettable flip-flop is much easier to design, and a lot of the time it may be even enough, right, to have it being resettable synchronously. But in some special cases, we require to have an asynchronous resettable flip-flop, which requires that we make some changes in the internal circuitry of the flip-flop. Just like we had resettable flip-flops, we can have settable flip-flops too. So for the settable flip-flops, whenever the set signal is 1, Q is set to 1. Whenever the set signal is 0, the flip-flop behaves as ordinary D flip-flop. So symbolically, we have this rectangle that represents the D flip-flop with D input, Q output, the clock signal. And then we have this extra set signal for it to make it a settable flip-flop. If we want to draw this or represent this more concisely, we can do it like this, and instead of set we just use S. Similar to resettable flip-flop, for the settable flip-flop we can have both synchronous and asynchronous settable flip-flops too. So the design for synchronous again is much simpler, so I can quickly draw it here. So if I assume this is the clock signal, this one is the Q output, this one is the D input, what I need to do is to basically pass the set signal with the data that we want to store and basically OR these two together. If set is 1, that makes the output here to be 1, which makes on the next rising edge of the clock Q becomes 1. When set is 0, then the output here is going to be D. So if D is 0, Q becomes 0. If D is 1, Q becomes 1. So that is a settable flip-flop. So in these past videos, we went over many concepts. We started with the introduction of sequential logic circuit. We said that sequential logic circuits, as opposed to combinational logic circuit, have the capability to store the previous state, and based on that previous state, the output is different. So they have memory functionality. So to get to this memory functionality, we said that we need to design some state elements that help us store the state of the system. We started with the bistable circuit, which was 2 inverters back to back. We said that it is a good start, but not perfect, because we didn't have any input to control what is being stored in the circuit. From that, we got to the SR latch, which we had 2 inputs, the set and reset, to control what is being stored. But we saw that there are some problems that are associated with the SR latch. We had this invalid state in which for when both S and R were 1, both Q and Q bar became 0. So this is something that we didn't want. The other thing was that we were practically using both set and reset to either set or reset one single output Q, right? And that was too much. We could have done it much easier or more efficiently. So then we decided to come up with the design for the D latch, which not only had the invalid case from the SR latch be completely eliminated, but also it gave us the capability to distinguish between the time at which we want some data to be stored and the actual data that is being stored, right? So that distinction was very important, something that SR latch could not satisfy. But we said even with all its nice properties, the D latch has a shortcoming too, and that was as long as clock signal is 1, the output can change based on the value of the input. So we said that let's just move further with this design the D flip-flop. So we only can change the output of the D flip-flop in a very short period of time. So D flip-flop basically samples signal D in the rising edge or the falling edge of the clock depending on the design that we have. So because of this, D flip-flops are more common in sequential logic circuit design. And then we said that we can combine a bunch of these flip-flops to create registers, and then in this video we went over some variations of the flip-flops that we can have. We can have enabled flip-flops, resettable flip-flops, and settable flip-flops, and we said these two can either be synchronous or asynchronous types, and we went over some of the design as well. So by no means all the topics that we have covered here are all the possible types of registers, flip-flops, latches, but they are a good foundation for us to start thinking about how we can design synchronous logic circuits. So as a final note, I highly suggest you take a look at JK flip-flops and also T flip-flops. So they are also very useful in designing synchronous logic circuits.